Okay, so we were looking at this translation from LTL formula to generalized uh, Bushy automaton over words, right? Uh, so one of the things that we noticed, of course, is that the size of the this DNBW, this is uh, exponential in the size of the LTL formula, right? Uh, so which is much smaller. Like instead of LTL, had we started, if we had started with S1S, like the monadic second order logic with one successor over words, then we saw that the automaton that we constructed, the NBW that we constructed, that had like a tower of exponentials, right? Like, and then we also say that this that in some sense cannot be avoided because there were lower bound results. We did not look into the lower bound results in details, but yeah, we look at the construction. Whereas in this case, when we start with LTL formula and we translate this into generalized non-Bushy word automaton, we see only an exponential blow up, right? And uh, one of the things that we mentioned, like when you go from alternating Bushy word automaton instead of an NBW, then we had an ABW whose size is polynomial in the size of the LTL formula. And of course, when you were removing the alternation, then you get an exponential blow up. But we also say that the ABW, it's a very weak alternating automaton. Okay, it's a very weak alternating automaton. And for that, you can actually remove the alternation with a blow up of only n times 2 raised to n, right? And here you are getting 2 raised to n, the size of this is like the GNBW that you are constructing is like 2 raised to n, right? So where n is like, okay, maybe it's written here, it's right. So it's like this, yeah, we can see here. And uh, but one thing to notice is that this is a GNBW, right? Whereas when we were removing the alternation from the very weak alternating automaton, what we ended up having was an NBW. Now, from the GNBW, if you again construct an NBW, there will be a small blow up, right? There will be a linear blow up, which we saw, right? It depends on the size of the acceptance, like the size of the acceptance condition, right? The number of accepting sets in the GNBW. So, right. So this is just a remark. So what we were doing is like we were translating, given an LTL formula, we were trying to construct GMW, right? So by the way, so I would also like to note that this the notion of LTL, linear temporal logic, it was introduced by Amir Nueli. Uh, it was possibly around like the late 70s. We should double check. I think around 1977. And Amir Nueli received the Turing Award for his work on linear temporal logic and other related things. Okay, so he went ahead to receive the Turing Award, and we are also looking at this other construction, right? This construction that we are looking at, which is this Vardy-Wolper construction, which also received the Gödel Award. So these works that we have been studying now, they have like really very strong implication in entire computer science, theoretically as well as their applications in the industry, right? So that's just one thing as a small remark. Uh, so okay, so now let's try to recall the construction that we had, that we were studying, right? So what this formula, what this theorem essentially says, that given an LTL formula phi over the set of atomic propositions, so we construct this GNBW over the alphabet uh, two ways to, I mean, the power set of this set of atomic propositions such that the set of words which satisfy phi is the same as the is language which is accepted by this automaton A phi, right? And this can be constructed in this exponential time. So in fact, the size of, as we were mentioning, the size of this automaton is exponential in the size of the formula. And the number of accepting sets is bounded uh, above. I mean, this is linear in the size of the formula, right? The number of accepting sets. And how did this automaton look like? So we studied these elementary sets. So what were the elementary sets of formula? So this, like, you consider the for given LTL formula phi, and we considered like the closure, right, or the extended closure of this formula phi, and the elementary sets were essentially these sets of subformulas of phi which were consistent, like consistent with respect to propositional logic, and they were also maximal, and they were also uh, locally consistent with respect to the until formula, right? So now, and the initial set of states where those elementary, the set of all these elementary sets where the given formula phi belongs to the elementary set, right? And the set of accepting states, this f phi 1 until phi 2. So here phi 1 until phi 2 is a subformula which appears in phi, right? Corresponding to every phi 1 until phi 2, we have such such an accepting set, right? And how is it defined? It's defined as those betas, those sets of betas, such that either phi 1 until phi 2 is not in beta or phi 2 is in beta, right? Either phi 1 until phi 2 is not in beta or phi 2 is in beta. So if it is the case that you have like just phi 1 until phi 2 is there, right? But and you don't see the phi 2, right? You have phi 1 until phi 2, you don't see the phi 2, but you are only seeing the phi 1. Then that will not lead to an accepting run, right? Those are not accepting states, right? Corresponding to phi 1 until phi 2. Okay. Now, and how about the transitions? So you have, like, for example, like if we have a letter A, and in for an elementary set beta, which is like a state in the automaton, so in the transition delta of beta comma A, we have it's essentially the set of elementary sets beta prime, such that if for every xi belonging to the closure of phi, we have xi belongs to beta if and only if psi belongs to beta prime, right? So you have the transition, you have xi belongs to beta, and you will have a transition from this beta to beta prime if and only if psi belongs to beta prime, right? So that's the thing. And then if we have phi 1 until phi 2 in the closure, for every phi 1 until phi 2 in the closure of phi, we have phi 1 until phi 2 belonging to beta if and only if either phi 2 also belongs to beta, or we will have a transition to those beta prime where phi 1 belongs to beta, and as well as we have phi 1 until phi 2 belongs to beta prime, right? So this is how we define the transitions, right? And then we were doing the correctness of the translation from logic to automaton. So essentially what we are trying to prove is that this automaton that we constructed, the automaton A phi, it accepts exactly the same set of words which satisfy the uh, the formula phi, right? Clear? And so we started with one direction, which is that if there is a word which satisfies phi, then it is indeed accepted by the automaton A5, right? So we are trying to show that there exists an accepting run, right? This is a GNBW, so it's a non-deterministic automaton. There can be several possible runs. So we are showing that there exists an accepting run in this automaton A5, right? Uh, so we start in the following way, that suppose there is a word W which satisfies phi, and we would like to show that there is this accepting run. And what do we do? So we collect the set of states, right? We collect the set of states in the automaton A5. So how are these states collected? Like, so we say state beta I is of the form, like it's the set of all these sub formulas that are appearing in the closure of phi, such that AI, the suffix starting from AI, it satisfies psi, right? So if the suffix starting from AI, it satisfies psi, so we collect all such sub formulas psi, and this set corresponds to one such elementary set, and we are collecting the states in this way, right? So you start from beta 0, beta 1, beta 2, like this. Okay, so we have collected the states, and what we prove is that, like, okay, this sequence, right, the sequence of states beta 0, beta 1, beta 2, etc., this indeed forms a run in the automaton, right? So this indeed forms a run in the automaton, and this is indeed an accepting run. So this is the proof in this direction. This is what we did, right? Yeah, for like the different kinds of sub formulas that you can have, right? For the different kinds of size that you can have, right? Like we indeed can show that you can have such an accepting one. Okay, clear? Any question so far? Any question? Okay, so yeah. Now we try to prove the other direction. So, right? So the converse direction, which is that indeed the language accepted, the converse direction. What is the converse direction? That is that the language accepted by the automaton is also included in the set of words which satisfy the formula phi, right? So now suppose, so in order to do that, what do we do? Suppose we consider a word which is of this form, W equal to A0, A1, A2, etc. It belongs to the language L of A5, and then we have that, suppose beta 0, beta 1, beta 2, like this is an accepting run. Okay, this is an accepting run, and we want to show that for all I, right, for all psi belonging to closure of phi, psi belongs to beta I if and only if the suffix starting from ai, it satisfies psi. Okay, so this is what we are. And why does this suffice? Because by the construction of the automaton, we know that the formula phi, right? The formula phi, it indeed belongs to beta 0, right? If this is the case, and because of this, it will also imply that A0, A1, A2, A0, A1, A2, yes, this entire word, the word W, it satisfies phi, right? So this implies that the word A0, A1, A2, etc., it satisfies phi. Clear? Is it clear? Are you able to follow me?
Yeah.
Okay. Yeah. So just be a bit responsive so that I can try to understand, like, yeah, whether you are following. Right. Okay. So and so how did we prove this thing? We started proving this thing using the induction on the structure of the formula, right? So we started with the base cases where you have like this atomic propositions, like we started with P, and then we say like, okay, if you have true, so these cases are quite trivial, and then we say like, okay, if you have negation of psi, then we are saying that, okay, negation of psi belongs to beta I if and only if psi does not belong to beta I. Then by induction hypothesis, we have that if and only if AI to AI plus 1, this suffix does not satisfy psi, and if and only if that is same as like saying AI plus 1, etc., it satisfies negation of psi, right? So similarly, you can do for the disjunction, and you can also do for the next psi formula, right? So if you have xi belongs to beta I, if and only if psi belongs to beta I plus 1, if and only if you have by the semantics of okay, so if and only if, so this is by induction hypothesis, we have AI plus 1, AI plus 2, so the suffix starting from AI plus 1, it indeed suffices psi, and then it essentially also by the semantics of LTL, we have AI plus 1, the suffix starting from AI, it satisfies xi, right? So this is the case for the next, and then we are now going to start with the case for the until, right? So this is what we did until the end of the last lecture, and we are now going to do it for the until formula, right? So suppose phi belongs to beta I, right? Phi is this phi 1 until phi 2, and we want to show that AI plus 1, AI plus 2. So this satisfies phi. Okay, so how shall we uh, do that? Like, so if phi belongs to beta I, then what are the two possibilities? Like, one possibility is like phi is, as I say, phi 1 until phi 2. This belongs to beta I, right? So one case is that you also have phi 2 belongs to beta I, right? If phi 2 belongs to beta I, then by induction hypothesis, we have, sorry, yeah, by induction hypothesis, we also have AI plus 1, right? So we are doing the structural induction, right? So this satisfies phi 2, and hence we have that AI plus 1, etc. This satisfies phi 1 until phi 2. Clear? So this case is easy. Now what if we have instead phi 1 belongs to beta I, but phi 2 does not belong to beta I, right? So this is the only other possible case, right? So by the construction of the automaton, we know that in the elementary sets, if you have phi 1 until phi 2 belonging to beta I, either this is one possibility, or the other possibility is that you don't have phi 2 in beta I, but you have phi 1 belonging to beta I, right? Now, again, by the construction of the automaton, what can happen? Like, so you recall that the transition was like, okay, so I am satisfying phi 1, I am satisfying phi 1 until phi 2, right? In this state, in the current state, which is, let's say, this beta I. So I will have a transition to the next state, right? To a successive state, which is beta I plus 1. And there, again, I am going to satisfy like phi 1 until phi 2 belonging to beta I, and so that's the thing, right? So I'm going to satisfy this, and whenever again successively what happens there, that either there you have to satisfy phi 2 or you have to satisfy phi 1, and then the chain continues. If you are not satisfying phi 2, then again by the construction you will have beta I plus 2, and there again you have to satisfy phi 1 until, I mean, the chain is complete, right? So now what we claim is that suppose if you have, let's say in this case, that phi 1 belonging to beta I, phi 2 belonging to beta I plus 1, then we claim that there should exist some j. We claim that there should indeed exist some j greater than I such that where you have that phi 2 has to belong to beta j. Okay, and indeed, now, so as I said, right, like, so the chain has to be there, and I'm saying that anyway, there should also exist some j where phi 2 should belong to j. Clear, right? And it's also the, and also by the construction you have for all k less than j, I have that phi 1 belongs to beta j, right? So this thing anyway, by the construction we have this thing, right? Like as I was saying, that this chain has to hold. And also what I want to prove, the main claim here is, what I want to prove, there should indeed exist a j where I should see indeed this where this phi 2 is holding in this state beta z. Now, can you say why this is true? Why this has to hold true? Like what happens if, suppose, for the sake of contradiction, I say that indeed there doesn't exist such a j. So which means, like by contradiction, if I say, assume by way of contradiction, suppose I say that there doesn't exist such a j. So which means that for all k greater than equal to I, if I have that phi 1 belongs to beta k, and here I should write, so you should, yeah, here I should write a k actually, right? For all k greater than equal to I, phi 1 belongs to beta k, and of course phi 1 until phi 2 also belongs to beta k, right? So suppose if this is the case, right, then why this is a problem? Like how do we reach the contradiction actually? Can you say? Is the question clear? Is the question clear?
Yes,
Yeah.
Like in this case, phi 1 until phi 2 can't be satisfied, right? So, like the run can't satisfy PK in some sense.
The run can satisfy PK, but I mean, okay, the construction is giving me something like this. The construction allows me to have, like, go to a next state where you are allowing this phi 1 to be there, but phi 2 not being there, as well as you are having phi 1 until phi 2 to be there. Like you, I mean, if phi 2 doesn't hold, and if phi 1 until phi 2 holds, right, then you will also have phi 1 to be holding. And I'm saying that, okay, my construction allows me to have such a chain, right? I can go to a successor state where also exactly the same thing happens. Then there is another state where also the same thing happens, and so on and so forth, right? Now, my construction allows me to have such a chain, such an arbitrarily long chain. It can just keep on holding forever. Now, if that holds, then where will the contradiction come from, right? I mean, we are trying to prove like that it is indeed the case that it's going to satisfy this formula phi 1 until phi 2, right? We are going to prove, but as a result of the contradiction, we are going to prove, right? First, we have to show that there is some contradiction. And what contradiction with what? Usually we prove a contradiction with some assumption that we would have, we started with, right? And what is our initial assumption? The initial assumption is that we have like what direction are we proving? We are proving this direction, right? That if a word is accepted by the automaton, then the word unit satisfies fine, right? If the word is accepted by the automaton, then we have an accepting run, right? So if we are trying to do a contradiction, then we should be able to contradict with the fact that this is indeed an accepting run, right? So now I say that, like, we started with the fact that this is indeed an accepting run, and if we always have this, are we going to contradict with the fact that that the run is not accepting?
So, what were the final states again? Sorry, I forgot.
Okay. So what are the final states? So what are the final states? Good. So the definition of the final states, it's like you have corresponding to every until formula, you have this set of final states, right? If you recall the definition of GNBW, generalized non-deterministic Bushy word automaton, right? So what in general, like how is the alpha defined in a GNBW? In a standard GNBW, how is the alpha defined? Can you say in a
It's
GNBW?
a tuple of K sets,
It's a
and
tuple of it's a right. It's a set of k states, k
yeah,
sets, k sets. Yes.
and the run is accepted if it visits infinitely many states in each of the sets.
Infinitely many, yeah, infinitely often each of the
Each of the
it
state
is visited, right?
sets.
And each
Yeah,
set is also a set of states, right? And I
yeah.
have k many such sets of states, right? And here, what is the k in the case of this construction of the automaton? What is the k here when you say k sets? What is the k here?
Like the number of phi one until phi twos in the
Exactly. The
closure
number of until formulas, right? The number
until
of
yeah,
until sub formulas that appear in your given LTL formula phi, right? So the
yeah.
number of such until sub formulas, right? Now, uh, now, and how are we defining this set F phi 1 corresponding to 1 until sub formula phi 1 until phi 2? How are we defining this set? These are those betas such that either the phi 1 until phi 2 does not belong to that beta, or if the phi 1 until phi 2 belongs to that beta, right, then this phi 2 also has to belong to the beta. Is it clear?
Yeah.
Right? So either, so it's a good state, it's an accept state corresponding to this set phi 1, corresponding to this specific until, which is of the form, let's say phi 1 until phi 2, corresponding to this until, the good set, the set of good states is defined as either the phi 1 until phi 2 does not belong to that state, right? Or phi 1 until phi 2 may belong, but in that case, the phi 2 also has to belong to the beta. Okay? The phi 2 has to
Yeah.
belong to the beta. Then it's a good state. Okay? And these are the, and you want these good states to be visited infinitely often for every
Hmm.
formula. For every such until formula, you want these good states to be visited infinitely often. Clear? So now, what I was saying is that now suppose if you get to see such states always, that for all k you are not seeing the phi 2, but you are only seeing the phi 1 until phi 2, and you are only seeing the phi 1 there, correct? Then you are not seeing the good states, right? You are, after a while, after this I, you are not seeing the good states at all corresponding to this phi 1 until phi 2. Clear?
Yeah.
Right? So then I'm saying that there is a finite I, right? There is a finite number I, after which I'm not seeing the good states at all. Correct? And in that case, then how do I reach the contradiction?
So the run is not an accepting run
So the run
because
is
we
not an
don't
accepting
yeah.
run. Exactly. So the run is, in that case, we see that the run is not going to be an accepting run, which contradicts with our basic, the initial assumption that we started with an accepting run, right? Suppose this is an accepting run. It just says then this run cannot be accepting, right? Then this run cannot be accepting. Hence, indeed, our claim is true that there exists a J such that, in fact, there will be infinitely many J's, such that if you indeed see, like, if for every I, wherever you are seeing this phi 1 until phi 2 to hold true, there should exist a subsequent J where you should see the phi 2, right? To, in order to have this state to be good. Clear? Right? Right? So, so now suppose given this I consider the smallest such j where phi 2 is in beta j. Right? The smallest such j. I mean, I can see maybe quite a few such j's where this beta, sorry, phi 2 is holding true. Quite a few beta j where phi 2 is holding true. I'm saying that give me the smallest such j. Okay? Right? And how do I, and now if I look at the picture, so it's like this, and it's like this, and I have, so I have some I, then I plus 1, etc., etc., and then there is a j, and I'm saying that here I have phi 2 holding true, and each of them here I have phi 1 holding true. Right? Right? And now if I just take an induction on this thing, on this line here, right? So I have phi 2 holding true. So I have at the position j, I have phi 1 until phi 2 holding true, right? Just by the semantics of LTL. By the semantics of LTL, it indeed says that if phi 2 is holding true here, then phi 1 until phi 2 also holds true here, right? So what it means is that the aj plus 1, if this satisfies phi 2, then this implies that aj plus 1, etc., this satisfies phi 2, phi 1 until phi 2, sorry, phi 1 until phi 2. Okay. Now we can also do this for aj minus 1, right? Now in aj minus 1, it's for this particular suffix, I have this satisfies phi 1, and also we had like this satisfied and starting from aj, this suffix, it satisfies phi 2, right? And now by the semantics, so this we get by induction hypothesis, right? This we get by induction hypothesis. Why? Because phi 1 was there in beta j minus 1, right? Phi 1 was there in beta j minus 1. By induction hypothesis, we get this suffix starting from aj minus 1, it satisfies phi 1, and the suffix aj, it satisfies phi 2, which we saw, right? And right, and how did we get this, that the suffix, and this is also by IH, because indeed phi 2 belongs to beta j, right? This is the claim that we have, right? So the claim that we have here is phi 2 belongs to beta j. So by induction hypothesis, we have this aj plus 1, etc., satisfies phi 2, right? And hence by the semantics of LTL, we have semantics of LTL, we also have aj plus 1, it satisfies phi 1 until phi 2. Clear? Right? And now, again, what we have is that we have aj satisfies the suffix starting from aj, it satisfies phi 2. The since phi 1 belongs to beta j minus 1, right? By induction hypothesis, aj, the suffix starting from aj minus 1, it satisfies phi 1. And hence, if I have it starting from the suffix starting from aj minus 1, it satisfies phi 1, and the suffix starting from aj, it satisfies phi 2. We have that the suffix starting from aj minus 1, right? This satisfies phi 1 until phi 2, right? And you can do it for aj minus 2 and so on. So all I'm saying that on this line, you can have another induction, and you can say that finally, what do I reach here is that the suffix starting from ai, it satisfies phi 1 until phi 2. Clear? Is it okay?
Yeah.
Right? So you have another level of induction, which is just something that you need to do for some k which varies from I to j. Right? Is it okay? Is the proof clear?
Yeah.
Yeah? Okay, good. So we showed what we were trying to show. So we were trying to show this thing. If psi belongs to beta I, then this satisfies the formula psi. as well as if this satisfies psi, then psi has to belong to beta I. So we proved one direction, that if psi belongs to beta I, then this indeed satisfies psi. Now let's prove the other direction, that if this satisfies psi, then psi indeed belongs to beta I. So let's try to prove this direction. So suppose this is indeed the case, right? We want to show that this phi belongs to beta I here. Now here phi, if you recall, we are looking at the until formula. The other cases we have, right? We are doing by structural induction, and the other cases we have proved. Now the thing is, how do you prove such a thing? How do you prove such a thing? It's not too difficult, right? So you just do let's go by let's go by the semantics of LTL now. What happens if you have this suffix ai plus 1, etc., it satisfies phi? So that means there exists a j which is greater than equal to I, such that uh, such that aj plus 1, etc., etc., it satisfies phi 2, and for all k such that I k less than j, we have that ak, the suffix, etc. So this satisfies phi 1. Okay, exactly. By the structural induction, we have now indeed that that if this is the case, then what can we say? If this is the case, what can we say here? What is the next thing that we can say? We can say that phi
Phi
2
2 belongs to,
beta j, right? And for
yeah,
all k, right, we have for all such k between I and j, we have phi 1 belongs to beta k, right? Correct? And
yeah,
right, and now you can apply the transition, like the way our the automaton was constructed, right? So how was the automaton constructed? If you recall, what was the thing? So if you have, for example, like the transition function was like this. So if you have here phi 1, right, in this particular, let's say a beta, if you have phi 1 belongs to beta, if you have phi 1 until phi 2 belongs to beta, then you should also, you will definitely have a transition to all those beta prime, right? Where you have like such that phi 1 until phi 2 belongs to beta prime, right? So you will have such a transition. It was like an if and only if condition, right? If we try to recall how it was. So just look at this part. So we are having a transition from beta to beta prime. Okay, so if you have phi 1 belonging to beta and phi 1 until phi 2 belonging to beta prime, right? So you have phi 1 until phi 2 belonging to beta, phi 1 also belongs to beta. Then also you have like a phi 1 until phi 2 belonging to beta prime. In that case, you will have such a transition, right, from beta to beta prime, right? So this is what I have been trying to say, right? So this is the thing. You have such a transition, right? So now, so what we are saying is that we have phi 1 until phi 2 belongs to beta if and only if this holds true, correct? Now you see that this thing, so I already have phi 1 belonging to beta and I have phi 1 until phi 2 belonging to beta prime, right? So because of this if and only, so this, if this holds true, then this has to hold true, correct? Right? By the transition relation. By the transition relation, what does it say? If it is the case that in my current state, if I have phi 1 belongs to beta, and if phi 1 until phi 2 belongs to beta prime, then phi 1 until phi 2 also has to belong to beta, right? So what I get is that now I get that here indeed phi 1 until phi 2 belongs to beta. right? Because of these two, phi 1 until phi 2 belongs to beta, right? And now exactly the same thing you can also do for the previous state, right? You can also do for the previous state, because here you had, like we had, right? We had, this is the case, we already had that for all I, for all k between I and j, we have phi 1 belonging to beta, right? So we, in the previous state also, I have phi 1 belonging to this beta, let's say right? So this in the previous state, if I have, if I call this beta j, then j minus 1, right? And here I have j minus 2. And now again, by the same thing, if I have this as well as this, then I can say phi 1 until phi 2 belongs to beta j minus 2. Here. And this, so again, I can use an induction here starting from j until I, right? And I can say that I can have phi 1, since it was already the case that phi 1 belongs to beta I also have phi 1 until phi 2 belongs to beta I. Is it okay? Is it okay? So we are done with this, with the proof. Any question? Do you have any doubt? Should we
No,
go?
sir.
Sorry? Yeah,
No, it's clear.
it's clear? Okay, good. Right? So so what did we do? We use the structural induction, and then we say like, okay, by the fact that the way we have constructed the automaton, the transition relation, we indicate that phi 1 until phi 2, this also belongs to this beta I, right? This phi 1 until phi 2 belongs to beta I. And then like, so this was our original thing, that for all I, sorry, for all I, for all psi belonging to the closure I, if psi belongs to beta I, if and only if this satisfies the suffix satisfies the subformula psi. Now, if we start with our original formula phi, then by the construction again, phi belongs to beta 0. If and only if, then we have that the word it would satisfy phi, right? So hence, indeed, if we have an accepting run, right? If we have an accepting run, then we have that the formula phi is indeed being satisfied by the word on which that the word that corresponds to this run, right? Okay, so that's the thing. Okay, so we proved now both the directions, that indeed first we proved that L of phi is a subset of L of A phi, and then we proved the other direction also, right? And hence this gives the correctness of the construction. Okay, right. So the size of the GNBA, as we saw, it is exponential in the size of the formula. Now let's try to sort of uh, draw one example. Okay, one example corresponding to this construction that we saw, maybe one or two. Okay, so this is just that the formula says next of A, right? The next of A. So again, what is the state space? The state space, it consists of the elementary sets, right? So what are we trying to do? We are trying to construct the automaton A phi corresponding to this formula x of A. Now, so let's do this closure of phi. So what are the closures of phi? So you have A, negation of A, xa, and negation of xa. Sorry, it was already written, and then what are the elementary sets? Can you tell me what are the elementary sets that we have here? What are the elementary sets that we have here?
A and next A. Like the multiple.
A and xa. Then
Then A and not XA.
very good.
Then not A and XA,
not A and XA, and
and not A and not XA.
not A and not X. Good. Okay. So let's look at, so we have four states. Let's say A, X, A. We have A not XA, right? We have negation of A, say, negation of A, negation, say, like this. Okay. And now, okay. So if I have, let's say, here I can have indeed, so these are my initial states, right? Because they have the formula pi a. And here, since I have the proposition which is the atomic propositions that hold here are, that is A, okay, and here I have the negation of A. So A does not hold true here. So the only thing that I can do is like an empty set. Correct? The transition on the empty set of atomic propositions, right? So, okay, why do I have a, maybe I should also say, why do I have a transition from here to here? Like if I have an XA, then I should go to some place where I satisfy A, correct? So I can go to this place, I can go to this place, correct? So this is again by the transition relation, if you recall. So if I have X of psi, I can only go to those states which will have psi, right, as a successor, which will satisfy psi, correct? So I can go here, and I cannot go from here, I cannot go to this state, or I cannot go to this state, because they don't satisfy A, right? Because there is an X of it. Clear? So this is fine. What about this? Now here I have A, so I can again make a transition on A, and I should not go to any state which will have an A. So I cannot have a self loop here, right? So I can go to this state. I can go to this state on an A, or I can go to this state on an A. Okay. Now here I will have a transition on the empty set of atomic propositions. And now if I have XA, then I should go to a state where I will satisfy A. Where else can I go? I don't think I can go anywhere else, right? So this is fine. What about the transitions from this state? What about the transition from this state? So what about the transition from this state? Like, um, can you tell me what are the transitions from this state? What are the transitions from this state? Like, where all I
Can
can,
go to not A and XA by seeing the empty symbol.
and I can also go to have a self loop.
Huh, yeah.
Okay, so this is the thing. So we have drawn the automaton. What have we not specified so far? What have we not specified so far?
Uh, Accepting stage.
The accepting states, right? We don't have any until here, right?
Hmm.
The GNBW, right? So indeed, the accepting sets, the alpha is empty. The alpha is empty. What does it mean? What does it mean?
That any run which is like infinite is accepting.
Any run is accepting. Why is it true? Why is it that? Why is it the case that uh, any run is accepting?
Oh wait, sorry. The intersection with alpha should be non-empty, right?
the intersection with alpha should be non-empty for each of the sets.
But it will be empty because alpha itself is empty.
But that does it kind of match our intuition that we have? Like, so for example, if you start from here, if you start from here, okay, now you see that any word, like it starts with A, right? And
Hmm.
so anything that is like, suppose a phi A, and then something like this, A, right? So I should write it rather like this because it's a set of atomic positions, right? Like this. All these words, even here also I should ideally have like this, right? Yeah. So these words should be accepted. These words should be accepted, correct? These
Yeah,
words should be accepted. But what you are saying doesn't really match with our intuition or what we think should be true, right? So let's see what.
hmm.
This word I can read from phi followed by an a here. I can indeed read it. If I have to read an a followed by a. What about phi? Can I read phi or a phi? Is it possible? Does it allow this? So if I have,
Oh,
this doesn't allow a and then followed by a phi. No, I can't do that. I cannot do an a followed by a phi, or I cannot do a phi followed by a phi, right? So these runs, there is no run on these words, right? No runs here, right? No runs. Also my GNBW, this alpha we see is empty. Then what is going like, I mean, something is not really matching, right? What is not true, or like, or is it true and then we are not interpreting something correctly? So if alpha is empty in a GNBW, right? If alpha is empty in a GNBW,
Since there are k many sets in the acceptance condition,
yes.
here there are no sets
Hmm.
in the acceptance condition, and hence the it is accepting no matter which state we are at. Yes.
Well, but why? I mean, because I mean, as she was saying that, like, you have, it says that. So okay, I mean, maybe let's try to see this. Like, it says that for all k belonging to alpha, right? For all such fk, right? For all fk, right? Fk is a set of these final states. It happens that you want that inf of r intersection fk should be non-empty, right? Now, does it hold true? This is the acceptance condition for GNBW, correct? For all fk. Now, if my alpha is empty, then
But yeah, it is like vacuously
it
true.
is vacuously true for GNBW. It's not true though for, if you say it's, if you consider an NBW and if you consider a GNBW, there is this subtle difference, right?
Uh,
In case of an NBW, it says that a run is accepting if like you have that only that set alpha, and then you say inf of r intersection alpha has to be non-empty. This is for NBW, right? In the case of
right.
GW, you have, in addition, you also have this, there is a for all quantification here, which becomes vacuously true when the alpha is empty.
Oh,
Clear? So then we are fine. Indeed, none of the states are really, they belong to, my f is indeed empty, my alpha is, sorry, my alpha is indeed empty, and hence it says that any possible run which is allowed in this GNBW, it's indeed accepting. Clear?
Yes, makes sense.
Makes sense? Okay, good.
yeah.
Okay, so now let's do this for this automaton. So I may not be able to do all of it, but okay, I'll try to just sort of see how much I can do. Like it's slightly bigger. So I have A until B. I have A B in the closure. I have A B negation of N negation of B. I have the phi and the negation of the phi, right? And what are my betas? Like the elementary sets, I have A B, A until B. Then you can just negation of A, I can have this, I have A until B, I can have another one, which is like negation of B, A until B, I can have negation of A, negation of B, negation of A until B. This is also allowed. I can have a fifth one, which is like A negation of B and negation of A until B. Okay, so I believe these are the ones I can have and nothing more. Right? So this is a thing. And now let's see what are the let me define the states. So right, and so yeah. Okay, so you just kind of look at them and you can at some point of time tell me which ones should be the final states, which ones should be the initial states, and so on. So I'll just try to draw the automaton. So let's say I have here, I'm writing the beta 1, A, B, A until B. Then I'd like to draw the beta 2 somewhere where, let me write it here, which is negation of A, B, A until B, right? So these are all like the sets, right? This is how ideally I should write them. Then I will have the third one, which is A negation of B, A until B. Sorry, this will be final state. Then I have the beta 4. So I have this. I have the beta 4, which is like negation of B, negation of A until B, right? And then I also have a beta 5, which is like this, A not B, A not B, not of A until B. Okay. So, right. Okay. This is this. Okay, so now can you tell me what are the initial states? So that is easy to see, right? Like I think whatever will have A until B, they are the initial states. So this is an initial state. This is an initial state. Then what else? This is an initial state. Correct. And what are the final states? What are the final states? Can you tell me? So I just have here one until formula, A until B, right? So what are the final states here?
The ones which have A until B.
The ones which have A until B. So is it a final state?
Wait, actually.
Is it a final state? So what was the definition of the final states? So it was like you should have either you don't have phi 1 until phi 2, either you don't have phi 1 until phi 2, or you should have the phi 2. You should have the phi 2, correct? So if
Right.
you have B, then it is indeed a final state. Okay.
Hmm.
If you have a B, then it is indeed a final state. So this is not a final state, but this is a final state, right? So let me try to draw this. This is a final state. What about this one? Is this a final state? Is
Yeah, because A
this is a
until
final?
B is not.
Because you have a negation of A until B, right?
Yeah.
Negation of A until B. So if A until B is not there, then it is good. I mean, it's a good thing. Okay, it is okay, right? So if you, is it okay? Do you want to recall again how we defined, right? Either phi 1 until phi 2 is not there, or phi 2 has to be there. Either it is
Hmm.
not, or phi 2 has to be there, right? So it is not there. So we are fine. Okay. What about this? This is also a good state, right? So I can, this is also a good state, right? Now, what about this? This is also good because indeed I have the phi 2 here, right? So this is also good. So only one which is not good is this one, because you have this as well as you don't have the B, right? So this is not good, right? So all the remaining 4 are finally good. And these 3 are initial. So now what are the transitions like? So here, what is the transition that I would have? What is the letter on which I will have a transition on this, from this state, for example? What is the letter on which we have a transition? What is the letter that we on which? So what is the, so a letter, so what is the sigma here, right? What is the sigma?
All possible subsets of A, comma B.
Yeah, exactly.
Like
It was,
empty singleton A.
yeah. So this is the sigma, right? And now from this state, what are the possible letters which are allowed? For example, from here we said only A is allowed. From here you have the empty set is allowed. What about this? What is being allowed here? What is the letter that is allowed here? What is that set?
A, comma B.
A comma B, exactly. So A comma B. So you have here A comma B. Okay, I can have A comma B here, which is a transition, right? I can come to here, right? I mean, this does not, for example, like I will add everything unless it is something which is kind of disallowed, right? So I can have A comma B, and it's still okay. I can reach somewhere, all right? And yeah, this is fine to have. And I can also have here, I can go here, A comma B, I can reach here. I can reach here also with an A comma B, right? A comma B. I can also go here with an A comma B, and I can also go here with an A comma B. It's nothing which really restricts me. Okay, so I have all these things. So essentially all these things. Now, what about from here, let's say, from here, okay? Or not a B, yeah, let's say from here. So this is my beta 2, let's say, okay, let's see. So here I have only B I can do, right? So I can do a B here, okay? Now, I can also do I can also, so here, what is the thing? like I'm saying that I have A until B and I'm satisfying, I already satisfy that here because I have a B, and I can go with a B here. This is fine, right? And I can also go with a B here. This is also okay. And I can go with a B here also. Like this is also fine. What about here? I mean, I can do a B here too. Doesn't really restrict me. I can do a B here. Okay. So all this is good. What about my uh, um, okay. I mean, okay. So um, just maybe just try to recall something here. So if I have, for example, in this particular case, if I have A until B, right? This is belonging to, let's say, beta, here it is beta 1. This was my beta 1. So this is equivalent to saying that either B belonging to beta 1, right? So which is already the case here, or you should have A belongs to beta 1 and A until B belongs to beta prime, right? So this is just, I mean, this we will see under, I mean, why I'm writing this is because that for some cases it may hold that it is going to restrict some of the transitions, right? Like so, let's see. I mean, we'll figure out like which is not allowed. And so far we found that from these two states, at least from the beta 1 and from the beta 2, I mean, I have transitions to all other states, like to every state. And what about the following? Like now, this is my beta 3. Let's go for this. If I try to write this, uh, I should have like A until B belonging to beta 3, right? So this is like A belongs to either beta 3, right? And since I don't have the I don't have here B is A until B, so B doesn't hold true. So I have to have A belonging to beta 3 and A until B should belong to beta prime, right? So, uh, right? So I'm doing now an A, so I can do an A and I can only go to those states where A until B is there, right? So let's do that. So I can do here an A, but now you see, I cannot go on A. So from this particular state, only a transition on A is allowed. But I cannot make a transition to this particular state. Why? Because A until B is not there in the successive state, which is beta prime. Here, A until B is not there. So I cannot make a transition like this. Okay. But I can make a transition like this. Here A. Because you require that A until B has to be there in the successive state. Okay. So that's the thing. I can also go here. Okay. And then I cannot also go here. So I have this, I cannot go here, I cannot go here because of the negation of the entity. Is it clear? Was it clear?
Yeah.
Right? So why I'm writing these things, just to figure out like which transitions are allowed and which transitions are not allowed. This, given the fact that A until uh, given the fact that A until B belongs to beta 3, right? Given that B is not there in beta 3. Since B is not there, so I have to satisfy A belongs to beta 3 and A until B belongs to beta prime, where beta prime is a successor. So A until B has to be there in the successor. So I cannot make a transition on A here to this as well as to this, but the other ones are allowed because they have the successors. Whichever state has A until B, I can make transition to those ones. Okay, so now I am left with the remaining two, beta 1, 2, 3. This is my beta 4. This is my beta 4, right? And beta 4, now this one, if I say A until B, A until B, this does not belong to beta 4, correct? So this means this is same as saying that B should not belong to beta 4 and it should not also be the case that A belongs to, it should not be the case that A belongs to beta 4, or so I'm just negating such a thing, right? Like, so essentially, or A until B should not belong to the beta prime, where beta prime is a successor, right? Correct? So, right. So these conditions are fine, right? A does not belong to beta 4, B does not belong to beta 4. And so I can do pretty much, I can go everywhere because already the conditions like this is satisfied as well as this is satisfied, right? So I can, since this is satisfied here already, so I can do like a phi, I can do a phi here and I can go here on the phi, I can go to here on the phi, I can go to here on the phi, I can also go to here on the phi, right? So the condition is already satisfied here. Clear? And what else is left? So there is one more, which is beta 5. This is my beta 5, I think. Right? And from beta 5, I can do transitions on A. Okay. And so here for the beta 5, A until B does not belong to beta 5. So can you tell me what should I write here? So this is equivalent to saying B does not belong to beta 5. Of course, this is true. And A does not belong to beta 5, or A until B does not belong to beta prime, like this. Okay, so now here you see that this part is not satisfied. Like this is of course satisfied. B belongs to, sorry, I made a typo. B does not belong to beta 5. Okay, so of course this is satisfied, but I have that A is there in beta 5. So this is not satisfied. So I have to satisfy with this part, right? So I should only go to those places where the A until B is there. Okay, where I
A
have,
until B should not be there, right?
yeah,
In those.
that's what, yeah, again, you are right. Yeah, there was a typo. Yeah, there was a typo indeed. So it should be the case that A until B should not be there in the beta prime, right? So I should go only to those states, right? So now I have on A, I can do thus a self loop I can do, right? Because I go to the successor, the same state here where A until B is not there. And where all I can go? I cannot go to this state because there is an A until B. I can go to this state. So I can indeed go to this state with an A, and I cannot go again to this state from here. Cannot go. I cannot go here, and I cannot go here as well, right? So the only possible transitions, that means I have like these two. I can only go here and I have a self replication. Okay, so that kind of completes this example, right? So A until B. So see that such a small formula A until B, but like there are so many things that we indeed need to take care of when we are constructing the automaton. Okay, right? So any question on the construction of the GNBA, GNBW? Is it clear, the construction? So I think it will
Yeah.
become, you will be more familiar. I mean, you should try it out yourself once, right? I mean, so that yeah, you become more sort of used to such constructions from the uh, from a given formula. I mean, there are so many subtle things. How do you define the like define the acceptance set? How do you define the transitions? Like, right, there are these if and only if these kind of things for the transitions. You have to define the set of elementary sets, right? And yeah, like and then understanding that, oh, if there is no accepting if the set of accepting the set of sets of these accepting good states, right? If that is empty, then in the case of GNBW, it indeed accepts all runs and so on. And once you construct the automaton, then you of course understand like what does A until B mean, and then you should try to start from here and then try to follow the run on an input word, and if you and should try to convince yourself that it is indeed visiting all the good states, not all the good states, but the good states from each set, right? Each set that fk, each of these fk sets infinitely often, right? So you should try to do it yourself and convince yourself and make yourself more familiar, right? I mean, there are so many small components that there is always a chance that one can do something wrong. Okay, so I will do this last thing before we finish today. Is indeed like there is a lower bound for constructing an NBW from uh, LTL, right? So indeed, what we can show is that there exists a family of LTL formula phi n, okay, and such that the size of the formula, it is polynomial in n, but every NBW that you can construct corresponding to phi n, it has at least 2 raised to n states, right? So the size of the formula is polynomial in the uh, is polynomial in n, and whereas every NBW will have at least 2 raised to n states. Okay, so how do we do such things? So essentially, I can consider any set of atomic propositions such that the set of atomic propositions should not be empty. Okay, it should be a non-empty set of atomic propositions, such that if you consider the power set of all subsets of such atomic propositions, so this should have a size of at least 2, right? So for example, like if you have only A, this is your AP set of atomic propositions, right? Then you have the empty set as well as the A, correct? Correct. So these are your like these are the letters that you have. The size. This is the alphabet, right? So the size of the alphabet should at least be 2 is what we are saying. And now you consider the family of languages where you have this ln, and how does it look like? You have a suffix here following this part. So this part is like A1 to AN and A1 to AN. Like, so you have a U here followed by a U, where U is a finite string, right? U belongs to sigma star, correct? U belongs to sigma star, and then you have a W, which is an infinite suffix. So W belongs to the sigma omega, right? W belongs to sigma omega, and we are defining our ln like this, okay? And we can define this this set of such words, the language, using a simple LTL formula, right? How does it look like? So it's like you have over all the letters, you take a conjunction, right? And you have such a thing like, which is for all I from 0 to n. I'm saying that x of I, what is x of I? X of I means x repeated I times. So if you have xx, it means your successor's successor, right? So two steps from now, so if it is at time I, you are talking about at time I, then at time I plus 2, you should have a. At time I plus 2, you should have a. That's what it means, okay? Now, it essentially means this one, it says that xi of a, for every I, it's equivalent to xi plus na, where a is some atomic proposition. Okay, and this has to be true for every such atomic proposition, right? So this formula, you can clearly see that this indeed it describes this language, right? Okay, any question on this, on the formula and the language? Is it clear? Is it okay? The definition of the formula and the language?
Yeah.
Yeah, right, okay. So now what you need to show is that any NBW accepting phi n has at least 2 raised to n states. So how do you do that? So this is very simple, like, and it's the proof. It's just a very simple argument. How can you show this? How can you show this? Can you tell me the proof? So I'm saying a proof by contradiction. How can you prove this? So what will be the first thing that we write?
So like for each A1, A2 up to AN, we have like two choices for the atomic propositions, like AI and negation of AI.
Uh-huh. Sure.
So like, so all the words consisting of like say A1, A2, AN, then some other pattern like not A1, A2, A3 up to AN, all these after their N transitions will be at different states, right?
Okay. And if not?
And because if two of them end up in the same state,
Right.
then for the same prefix,
Hmm.
the word for the same suffix, the words will be
Hmm.
accepted, and that will give a contradiction.
Good.
So we will need at least two to then states.
Very good. Okay. So that is the idea. So proof by contradiction. Suppose you have an NBW. I'll just write. Suppose there is an NBW accepting ln, accepting ln. Okay. Let me with less than 2 raised to n states and accepts ln, right? So then what happens, like there are two strings u and v, such that, right, u and v, right? So we have two different strings u and v, right? That is, u is not the same as v. Then what happens by Pigeon hole principle? we have that starting from some initial state, because there are 2 raised to n many such strings. There are of length n, right? Since the size of the size of the alphabet is at least 2, there are at least 2 raised to n many such strings of length n starting from some initial state. By 2, there exist, right, 2 different strings starting from some initial state. By reading u and v, we reach the same state q. Correct? So suppose u is a1, a2, dot 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 an, and this is a1 prime, a2 prime. So this is my u, this is my v, an prime, right? Now, correct? And then what happens is, like, if it is the case, now if it is the case that a1, a2, after reading this word u, so there should be some accepting, if there is an accepting run from the state q, right? Like if this is accepted, yeah, if, like, okay, or maybe I should just write this here. If the suffix a1, if the suffix a1, a2, a up to an followed by w, where w is an infinite string, is accepted from q, then the NBW accepts a1 prime, a2 prime, an prime, a1, a2, an w as well, right? And this is a contradiction. So this is a contradiction. Clear? Right?
Yeah.
Okay, so I'll stop here, and we will need one more class for finishing LTL. So what we will do is, in the next class, we'll do the complexity of LTL satisfiability and model checking problem. And also we will look at something which is quite interesting, which is what kind of properties you can express using LTL. So one thing we saw, that LTL can be translated like a formula phi in LTL, it can be translated to an automaton A of phi, an NBW A of phi, right? So which means that the words which satisfy a formula, LTL formula phi, this set of words, this is essentially a what? Omega regular language, correct? This set of words, it forms an omega regular language because there is a corresponding NBW, right? But what about the other direction? Given an NBW, can you also translate it to an LTL formula? In some sense, like, we are asking the question, are they equivalent really? So we'll try to answer this question in the next class, and also we'll try to look at the complexity of LTL satisfiability or model checking, which is essentially, we'll see that these are piece-based complete problems, right? So that's the thing. So before I stop the recording, any other question on what we discussed today?
No.
No? Okay. Good. So then let me just stop the recording.